Unit 1, Lesson 2. Understanding limits graphically and numerically. Topic 1.2, Defining limits and using limit notation. Limits are the backbone of understanding that connect algebra and geometry to the mathematics of calculus. In basic terms, a limit is just a statement that tells you what height a function intends to reach as you get close to a specific x value. Recall from pre-calculus that you evaluated 3 types of limits. Complete the table below. So if we were talking about a right-hand limit, I don't know if you guys remember this, hopefully you do. The limit as x approaches c, we put a little plus sign here, meaning it's approaching c from the right of the function f of x. And verbally, we would say the limit as x approaches c from the right, okay, for that function f of x. Left-hand limit, the limit as x approaches c, we put a little minus up here, from the left of f of x. Limit as x approaches c from the left, dot, dot, dot. A general limit, meaning it's not one hand or the other hand, it's not a left hand or a right hand, is just the limit as x approaches c of f of x. And that is limit as x approaches c. Now, for this general, you have to look at it from the left and the right. And for this limit to exist, it has to be going to the same y value from the left and from the right. Let's begin our discussion of limits by analyzing a rational function and examining the graph. Use the equation for f of x and the graph of the function to analyze completely. So we've got a function, it's a rational function. There is a quadratic in the numerator and a quadratic in the denominator. I can see that the quadratic in the denominator factors x minus 3 times x plus 3. And then up here, I'm wondering if this factors and if possibly something would cancel. And since I'm looking at the graph, do you notice that right here you see where I bet the x minus 3 cancels? Because if x minus 3 cancels, you set that equal to 0, that means you have a hole at x equals 3. So that kind of helps us whenever we're getting ready here, because we know it's 3x times x. And since I'm thinking that x minus 3 cancels, because I can see the graph of it, if I put a minus 3 there, I've got a negative 9, and then this would be a positive 1, giving me a negative 8 in the middle. And positive 1 times negative 3 is going to give me that negative 3 for the third term. So yes, those x minus 3's cancel. So this simplifies to 3x plus 1 over x plus 3. Sorry, my plus signs are getting wiggly. I don't know why they're so wiggly. Okay. So this is your function, right? Only it basically looks like this function with a hole, okay? So what did we do? Well, sorry, we factored and simplified. So this was our 3x plus 1 times x minus 3 over x minus 3 times x plus 3. So there was our factoring, and we canceled, giving us the 3x plus 1 over x plus 3. And then coordinates of the hole. Well, if I wanted to know what the coordinate is, because it looks like it's kind of in between 1 and 2 on the y-axis, right? So, because I know that my point is 3 comma something for the hole, I just don't know what the y value is. I am going to plug that 3 into this right here to find out what my y value is. So I'm basically putting that 3, if you want to, I'm putting it in for the x here, and I'm putting it in for the x here. Okay, and so 9 plus 1 is 10, and 3 plus 3 is 6, and we would reduce that to 5/3. So this is going to be the 0.3 comma 5/3. And then what is the domain? Well, you see that it will accept any x value except 3 and where this asymptote is. Okay, it won't accept an x value at 3, and it also won't accept an x value at -3. So our domain is going to be -infinity to -3, union -3 to 3, union 3 to infinity. And then our range, if you remember, if you look at just this piece of it, and I guess I'll do that in a different color also, but if I'm looking at just this, it simplifies to 3. That means that y equals 3 is your horizontal asymptote. And so that means that your function will be approaching 3 for the y. So it's going to be -infinity all the way to 3, union 3 to infinity. So our range, -infinity all the way to 3, union 3 to infinity. Vertical asymptote, we said, was at x equals -3. So our vertical asymptote is at x equals -3, and we said our horizontal asymptote was at y equals +3. Okay. Understanding limit notation. So let's revisit, the notation we learned in pre-calculus. We need to convert these old methods of explaining extreme behaviors into limit notation for use in calculus. So example number 2, use the graph to complete the table below. So we're looking at a graph. We don't really have what the function is. We're just going to look at, as x approaches -infinity, the graph of f of x approaches. So think about, you're putting an x in, you get a y. You're putting an x in, you get a y. And I'm doing that like I put this x in, I get this y. I put this x in, I get this y. My x's are approaching -infinity. If I kept doing this, my y values are approaching 3. And so if I wanted to put that in limit notation, I would say that the limit as x approaches -infinity on the function f of x is 3. As x approaches +infinity, the graph of f of x approaches. So again, if you put an x in, you get a y. Put another x in, you get another y. Put another x in, you would be getting another y. And you can see that these values are approaching 3 from the bottom, from below. But this is still also 3. And so what would that look like as a limit? The limit as x approaches infinity for this function is 3. Remember, on limits, the answer is always your y value. What is your y value doing if your x is doing, what the limit is asking? So as x approaches -3, so let's say, and it says from the right. So let's say I'm approaching -3 from the right. So I put this value in. Look where my y is. I put another one approaching -3 from the right. Remember, I'm coming in this way towards -3. I put this y, or this x value in, I get this y value. Do you see how my y values are going to -infinity here? So this is going to be -infinity. So it's going to be the limit as x approaches -3 from the right, means we'll put a little plus sign, of f of x equals -infinity. As x approaches 3, and this time from the left. So here is 3. If I'm approaching from the left, I'm coming in like this, I get a y. I put this x in, I get a y. So I'm coming in towards 3 from the left, and my y values are approaching, well, this is the same function that we just were looking at. So my y values would be approaching 5/3. So that means my y values are approaching 5/3. So we would write it as the limit as x approaches 3 with a minus sign there from the left of f of x is 5/3, even though there is not a value at that point because there's a hole. As you're approaching it, it's approaching 5/3. So that limit does exist. As x approaches -3 from the left, so if I'm approaching -3 from the left, I'm coming in this way, like I'm going to be approaching it from the left. So if I put this in, there's my y. I put this x value in, there's my y. You can see that your y values are approaching positive infinity. This one's going to be positive infinity. And we would write this as the limit as x approaches -3 from the left, would be a little minus sign there, of f of x equals positive infinity. And then as x approaches +3 from the right, so for that one, we're coming in from the right, there's my y, put another x in, there's my y. You can see that from the right, it's approaching 5/3 again. So the limit as x approaches 3 from the right of f of x is 5/3. So can you explain what the value of a limit represents in terms of the graph? So I want you to just stop and think about that. Look at the graph, think about what the answers to these limits were and what the value of a limit represents in terms of the graph. See if you can get some sort of answer in your head, and then come back and we're going to look at that the limit is the y value. That the graph is approaching from both the left and right sides of the target value x equals c. The limit can occur at a hole and I'm going to put that in quotes, a removable discontinuity. I don't know if you remember that from last year, but holes are considered removable discontinuities. So let's look back here. I don't know if you remember from last year, but if your left-hand limit and your right-hand limit go to the same value, then your limit exists. So when you're looking at these two limits, one is approaching 3 from the left and it's 5/3, one is approaching 3 from the right and it's 5/3. So we could say that therefore the limit as x approaches 3, you know, just plain old limit, general limit of f of x is 5/3 because the left-hand limit is 5/3 and the right-hand limit is 5/3. When we're approaching -3 from the left and the right, this one right here, from the right it's negative infinity, from the left it's positive infinity. So for that one we would say, and I think I'm just going to go over here. We would say that the limit as x approaches negative 3 of f of x equals dne. And remember, that stands for does not exist. Okay, that limit does not exist because the left-hand limit does not equal the right-hand limit. We always say why. So because the limit as x approaches negative 3 from the left of f of x does not equal the limit as x approaches negative 3 from the right of f of x. It's really easy to forget to put your function in a limit. It's really easy to forget this and to forget that and or that. And this was a plus sign. I can hardly see it. Please make sure that you're writing your limit properly, okay? It has to have LIM, it has to have x approaching some value, and it has to have the function there. Okay, so informally, a limit is a y value, which a function approaches as x approaches some value. So the limit as x approaches c of f of x equals L means as x approaches c, f of x approaches the y value of L, okay? And you guys probably remember that from last year. I'm hoping. So let's go ahead and go to the next one. 1.3 topic, estimating limit values from graphs. Consider the function shown at the right. Say you want to find the limit as x approaches 4 from the right of f of x. The positive sign in the limit notation indicates a right-hand limit. If you think of the function as a highway and imagine you are traveling along the graph of f of x toward x equals 4 from the right, okay, so it's almost like you're in a car. Oh wait, sorry, here's 4. You're in a car on this highway and you're traveling towards that value from the right, okay? That's what you want to be thinking of. What y value is your function approaching? And you can see that your function is approaching 3. So it says, and you stop at the vertical line, x equals 4. The y value where you stop is 3. Therefore, the limit as x approaches 4 from the right of f of x is 3. Because you're coming in, you're approaching it. You can think of it also as you're putting values in. Where's the y value? I'm going to put another value in close to 4. Here's my y value. And your y values are approaching this final y value of 3. So that's why the limit there is 3. Okay, so now, example number 3. Use the graph above to evaluate each of the following limits. If you feel like you remembered this from last year, you should stop the video right now and you should try and answer A through N. And then come back and see if you got them right, okay? So let's do A, f of 2. So if I look at 2 here and I look where the solid dot is, the solid dot is at negative 1. So my f of 2 is negative 1. What's f of negative 1? Well, I go to negative 1 and then I go up, and you'd think it might be 2, but that's an open circle. The solid dot is up here at 4. So f of negative 1 is 4. The limit as x approaches 4 from the left. So if I'm approaching 4 from the left, like I put a x value in, I get a y. I put another one in, I get a y. You can see that as you're moving this way, your y value is approaching 3. So this one is 3. The limit as x approaches 2 from the right. So here's 2. I'm approaching from the right. So here's the y value. Put an x in. Here's the y. Right? You're approaching it from the right. You're coming in this way. You can see that it's approaching 1. It doesn't have to equal 1 at 2. It just needs to approach it, right? That's a limit. So it's approaching 1. The limit as x approaches 2 from the left. So if I'm putting in values on the left-hand side of 2, look where my y's are. So I put in an x, and now here's where my y is. So you're coming in this way, approaching 2 from the left, moving along this way. You can see that you're approaching -1. So for this one, it's -1. Notice that this is a left-hand limit and a right-hand limit. They don't equal the same thing. So from those two things, you know that that limit is not going to exist if it was just a general limit. The left-hand limit exists, the right-hand limit exists, but the general limit does not, because the left-hand limit does not equal the right-hand limit. Letter F, the limit as x approaches -1 from the right. So I'm approaching -1 from the right. So I'm putting values, and there they are. And so basically you're moving this way along the function. You can see it's approaching 2. So this one is going to be 2. Oops, sorry. Put it at the wrong one. And now the limit as x approaches -1 from the left. So here I'm approaching -1 from the left. Put a x in, I get a y. So I'm getting all these y values. I'm approaching it from the left. I'm going this way. I'm still going to get 2, even though it's not. It's an open circle there. I'm still approaching it, and it's 2. So since this is my right-hand limit and my left-hand limit, they are equal to one another. This limit, the general limit as x approaches -1, would exist because they both equal 2. It doesn't matter that the function is defined as 4. They're approaching on both sides, and this is considered a removable discontinuity here at x equals -1, and so the limit would exist. Okay, H, the limit as x approaches -4 from the right. So -4 coming in from the right, and you could see that your values are approaching 2. The limit as x approaches -4 from the left. Well, that limit is going to not exist. This one does not exist because I can't come in from the left. If I'm coming in from the left, there's no function for me here. I put this x value in, there's no function here. So I can't come in from the left. So that limit does not exist. So only at the end point, only the right-hand limit exists at this endpoint for this function. Limit as x approaches -1. Okay, this was the one where we looked at it from the right and it was approaching 2, and from the left it was approaching 2. Therefore, this limit exists, and it is 2. The limit as x approaches 2. Well, we looked at it from the right and it was approaching 1. We looked at it from the left and it was approaching -1. Therefore, this limit does not exist. And this is because the left-hand limit does not equal the right-hand limit. I just put that just to remind ourselves why it did not exist. And then the limit as x approaches 5, and this is just plain old 5. So I'm approaching 5. It doesn't matter if I'm coming in from the left or if because this is going to continue, or if I'm coming in from the right. Like if I'm coming this way or if I'm coming this way. That point right there, that the function's value at 5, it looks to be -2, is going to be the same either way. So this is going to be -2 because that's what the y value is approaching. The limit as x approaches 0. And so again, if I'm approaching 0, I'm looking at it as I'm coming in from the left, and I also have to look at it as I'm coming in from the right. So from the left, I'm approaching -1. From the right, I'm approaching -1. Therefore, this one is -1. The limit as x approaches 1. So again, I look at it from the left, so I'm coming in this way. And I look at it from the right, so I'm coming in this way. Either way, I'm going to hit negative 2. So this limit is negative 2 because the left-hand limit is negative 2, the right-hand limit is negative 2. So if we think of the function as a highway, then the point at 2, negative 1 could be considered the end of the road, while the point negative 1, 2 is more like a pothole. So I'm going to erase all the stuff that we put here so we can kind of look at it nicely. And you've got it on your paper, but you might have written things on your paper. So we're talking about the point 2, negative 1. So they're talking about this point right here. Could be considered the end of the road, while the point negative 1, 2 is more like a pothole. So that one is more like a pothole because the function continues on. You know, it's like you're on the road, you're on the highway. Oh, you dip into a pothole, but you continue on. Where once you get to this, the road ends. You can't continue on. So now they're saying, how would you describe the points located at 2, 1? Okay, so there's a point at 2, 1. This would be like a dead end without a barrier. Because that's an open circle there. What about 4, 3? So 4, 3. What about this guy right here? That to me looks like a very sharp turn. Because you are on the road. Let's say you're traveling on the road here, and then you have a very sharp turn, but you can at least continue on the road. Okay? So hopefully this analogy gives you a visual reference for understanding limits from a graphical approach. Because if you hit a dead end, that limit is not going to exist. This is, if you remember correctly, this is called a jump discontinuity. Because if you were trying to, you know, if you had your pencil along the function, you would have to pick your pencil up to get back onto the function. So therefore, there's a jump discontinuity there. And so your limit is not going to exist at that value, because coming in from the left, it's going to be one thing. Coming in from the right, it's going to be something else. Okay?